Imagine bridge columns that you see around when you drive, okay? All of those are monolithic, are cast in place elements. So these elements have very, very limited resistance to deformation, any deformation from any hazard. Earthquakes, in our case. What we're trying to do in this research, we're trying to introduce new response mechanisms within a column design so that we can accommodate this kind of deformations without damage. Compared to conventional cast-in-place systems where imagine the columns can be a single pour of concrete, so you have solid elements, rigid, that they're very, very resistant to motion. Here we have a totally different design where you have the column being broken down into segments. Essentially, the bridge column is already in pieces, so you can't break it down in pieces if it's already like that. So you hold these pieces together using tendons, and then you have specially designed joints along the height of these columns where we allow those joints to exhibit small controlled sliding. That sliding adds to the deformation capacity of the system. So you have a rigid column where if it moves a little bit, it gets damaged and it probably collapses. And then you have a column that it can move a lot without getting damaged. The whole idea of having these response mechanisms is to add to the capability of the system to deform without getting damaged. So that can be a game changer on how we design bridge columns.